All right, let's get into it. Today, we're going to try and crack a pretty fascinating puzzle in reservoir engineering, the horizontal well. I mean, this technology was a total game changer. But figuring out what it's actually telling us, well, that's like a masterclass in detective work. So, here's the big question, right? This is the central mystery. We're pretty good at reading data from a simple, straight-down vertical well. But the second you turn that well on its side, all of a sudden the language it speaks becomes incredibly complex. So what's actually changing down there? And how do we learn to understand it? That is exactly what we are going to unpack today. And here's how we're going to do it. This is our plan of attack. First, we'll look at the puzzle itself. Then we'll figure out why anyone would drill sideways in the first place. After that, the real fun begins. We'll hunt for what I'm calling the footprints of the fluid flow. Then we'll learn how to read the evidence on a pressure plot. And finally, we'll solve for the reservoir's deepest secrets. Okay, so first things first. Let's get to the heart of the problem. It really comes down to this massive gap between the neat and tidy world of our textbooks and the messy, complicated reality of what's happening thousands of feet underground. You know, a textbook equation, it likes to assume the rock is this perfect, uniform block. But we all know reality is just not like that. It's much messier. And the pressure data you get from a horizontal well is incredibly sensitive to every single one of those real-world details. The reservoir's actual shape, the well's exact length, the complex ways different fluids are moving around, and it's this sensitivity that makes our detective work so important. So you might be thinking, if they're so complex to analyze, why even bother? Well, that's a fair question. And the answer is because when you get it right, the strategic advantage is just enormous. Think about it. By drilling sideways, you can lay a super long well bore across a huge stretch of oil-bearing rock. This maximizes your contact area, and in thin reservoirs, that's a total game changer. It also lets you slice through a whole bunch of natural fractures, basically opening up new highways for the oil. And, maybe most importantly, it helps you push back against problems like water creeping up from below or gas pushing down from above, which lets you produce way more oil for a much longer time. All right, now for the really cool part, the detective work. To truly understand a horizontal well, you have to look for clues. Clues left behind by the fluid as it moves through the rock. We call these clues flow regimes, and they're basically the footprints that tell us the story of what's happening in the reservoir. What you're looking at here is pretty much the whole story of fluid flow over time. See, as the well produces, the way that flow is moving, it changes pretty dramatically. It goes through 3 distinct stages, and each of these stages, each of these flow regimes, leaves its own unique footprint in our data, giving us another piece of the reservoir puzzle. So what is a flow regime exactly? It's really simple. It's just a specific pattern of how the fluid is moving at a certain moment in time. Think of it like taking a snapshot of the action. So let's take a look at that first snapshot. Our first clue shows up almost immediately. Right at the beginning, fluid flows toward the well in the vertical plane. You can see it there in the top left part of the diagram. But here's the thing. Because the rock often has different properties going up and down than it does side to side, this flow isn't a perfect circle. It's actually an ellipse. We call this the early pseudo-radial flow, and that is our first major footprint. And here's clue number 2. After a little while, the flow pattern actually simplifies. As you can see in the diagram, the fluid starts to move in these straight, parallel lines, feeding into the well from directly above and directly below. This is our second phase, a nice, clean, simple, linear flow. Okay, our last footprint. This one doesn't show up until much later in the test. The flow completely changes again. It expands across the entire horizontal plane, almost as if the well were just a single point drawing fluid in from every direction around it. This is the late radial flow, and this one tells us about the reservoir's properties on a massive scale. So, we found our 3 footprints. Great, but how do we actually see them in the data we collect? For that, we use a special tool called a pressure derivative plot. This is how we translate those flow patterns into hard evidence we can actually work with. This plot right here, this is our evidence board. It's basically tracking how the pressure changes over time. And each of those flow regimes we just talked about, the early radial, the linear, and the final radial, it creates a unique, recognizable shape on this plot. If you know what to look for, you can literally read the reservoir's story right off this chart. Now zoom in on this straight line rising right here in the middle of the plot. This is the smoking gun. Its slope is exactly 1/2, and that, my friends, is the unmistakable mathematical signature of linear flow. When we see this half-slope line, we know we've confirmed our second clue. We know for a fact that linear flow is what's happening. And now, look all the way at the end of the plot. See where that curve just flattens out into a nice horizontal line? That is the signature of our third clue, that late-time radial flow. This stabilization tells us that the pressure response is now seeing the entire reservoir in the horizontal plane. It's giving us the big picture. So we've gathered the clues, we've decoded the evidence. Now it's time for the final step. It's time to use all this information to calculate the reservoir's most important secrets. This is the payoff. And here's how we crack the case. It's really cool. We actually work backwards through our clues. So first, we use that final flat line, the radial flow, to calculate the horizontal permeability. That just tells us how easily fluid flows sideways. Second, we take that number and we use it with our half-slope line to figure out the height of the well's perforated section. And finally, we go all the way back to the beginning data to calculate the vertical permeability, how easily fluid flows up and down. And the source material really puts it perfectly. It says, by using these 3 flow regimes, we can extract all the reservoir parameters and fully analyze the horizontal well behavior. It's not just a guess, it's a complete framework that lets us understand exactly what that well is telling us. It's just a really powerful method. So there you have it. We've cracked the code for horizontal wells, and it really makes you wonder, doesn't it? Now that we know how to read the story written by Fluid Flow, what other secrets about the deep earth are just sitting there, waiting for us to decipher them from the subtle language of pressure?
For advanced petroleum and energy engineering education, stay connected with us on web, LinkedIn, Instagram, and YouTube under the handle Teachdemy.